Well, hey everyone, welcome back to the bench. It's time for another installment to the Discrete audio amplifier design and build project. Now, because I need to get this on perf board so I can run it at full power, I can't really do that with these socket boards. I needed to get the amplifier circuit as I perceive it to be laid out here in a schematic. There are some changes from the original designs. I did flip the front end. The current sources are up here, current mirrors down here. It doesn't really matter. It could be flipped if I wanted to do it that way, but I'm just showing it this way. This circuit contains some protection circuitry, the fuses, rail fuses, and catch diodes. Those don't really need any serious design considerations, so I just drew them in. I am not showing the current limit circuit just yet because that circuit just sits there and does nothing until there's an overcurrent condition in the output stage. So as I put this amplifier on a perf board, I don't want to include that circuit. It's just wasting components, because if I have to do a lot of rework, I might have to start over again, and considering there's enough changes that need to be made to the schematic, so it doesn't make sense to throw those parts in. So if you go back to the very first video in the series, I was talking about what my goals were with this amplifier. Again, I wanted an amplifier with decent performance. I wanted 0.001% total harmonic distortion, for example, at least at 1 kilohertz. At like 20 kilohertz, I don't want to go over 0.01. I'm not going after the 0.00001 type stuff. It's just, I think it's really unnecessary. It's overcomplicated. There's a lot of parts to worry about and get stable. Fairly simple amp. I mean, it's not the most simple amp, to be honest, but there's a lot more simpler designs out there. Including the current limit, this circuit will have 15 transistors in it, just for one 50 to 100 watt amplifier. Some changes I made. These transistors are not labeled yet, but I think I'm going to use the, I believe it's the 2N, let me get my transistors, the 2N555 ones and the 5401. Yeah, 5401. Looking at the data sheet, they have plenty of collector emitter voltage rating, 160 volts I believe, nice linear gain characteristics. That way I can simplify the bill of materials. They'll be used in the input stage, some parts of the VAS stage. Okay, so I've taken this circuit, sans the protection devices, because like I said, I don't want to waste parts on a perf board, if I have to go back and rework it. And by the way, I really like this graph paper. The line pitch is the exact spacing of components, so you're drawing the circuit as it will be in life size. What is that, 1/10 of an inch or 2.5 millimeter pitch? So yeah, the amplifier itself is not going to be very big. It's going to be fairly compact, though I still have to accommodate the current limit, some diodes, and fuse holders. So yeah, it's going to be bigger, plus I need to have holes for mounting. The actual board will be probably more like this size when it's finished. And of course I will have the boards professionally made. It's not so cut and dry when you lay these things out. There's a lot of things you have to take into consideration. One thing is inductive coupling. The output stage will conduct a lot of current, and you don't want that coupling back into the smaller signal parts of the amplifier. But I did have to run some lines under the output emitter resistors and the inductor coil. So what I did, I ran those as perpendicular as I could so they won't inductive couple. Plus, they'll be running under these devices, which are fairly high up off the board. Well, not that high, but there'll be a line running under these devices on the other side of the board. Another thing is capacitive coupling. Now there's going to be some very large voltage swings on certain parts of this amplifier, especially in the output stage and the voltage amplification stage, and you don't want that coupling to other parts of the circuit. But one thing to consider though is this whole area of the circuit, this side of the transistor collectors, the biasing part, the output transistors except for their collectors, of course the output circuits, emitter resistors, all that stuff, the voltage is going to be swinging together. There's only a couple diode drops of voltage difference there could be. That voltage is not going to change relative to one another. Now it will change outside of that, so you want to watch the capacitive coupling on other parts of the circuit, like back to the input stage, or parts of the current source over here. So I'm not so worried about capacitive coupling with these parts of the circuit together. Next thing is power and ground traces, laying those out properly. As you can see up here, I have the power supply bypass capacitors. These are not filter capacitors. The filter capacitors are the large capacitors that will be on a separate board. But the amplifier board itself must have bypass capacitors for the power supply. And I wanted to orient those in the middle of the board, and then I would have separate power supply line going out to the output stage, and another line going from the capacitors to the smaller signal parts, which would be the VAS and the input stages. Same with the ground. Smaller signal parts of the circuit have its own ground, and the output stage has its own ground. The return for the speaker, and of course the power supply ground line itself. Now I could put a resistor on each rail between the output stage and the smaller signal parts of the amplifier, and then another bypass capacitor. Don't really think I need that, because the way I have the capacitors oriented now should really take care of that noise on the power supply rails. And I don't want to overcomplicate the circuit if I'm not going to get a lot of benefit from those parts. And finally is shields. I'm not really showing it here, but I'll run some ground lines around here to shield some parts of the circuit. Of course, when I have the board professionally laid out, I'll be able to flood fill some areas with ground that will help the shielding as well. So that's basically it with the preliminary design layout of this amplifier. I need to actually order some more parts to be able to build this thing up. Hopefully I can get something started here in an upcoming video. Okay, so now I have a basic idea what this amp's going to look like, but now I already want to make a change. And it's not going to change the schematic or anything, it's just going to change the current. And that is the current that flows in the VAS stage. Initially I was thinking it would be around 10 milliamps. Now it's good to have a surplus of current, but you don't want to have too much for a couple reasons. One, higher current can mean more distortion, potentially more distortion. Another problem is these transistors, this current source and this amplifier transistor, sitting idle, they're going to dissipate about 1/3 of a watt. It's 10 milliamps times 35 volts. So they'll dissipate about 1/3 of a watt. Well, that's nothing serious, but I'd still want to run them a little bit cooler. I'm thinking of backing this down to like 6.5 milliamps. And the reason I chose that number is this resistor here. In my test where I was playing with the current source, I think I was running a 68 ohm resistor which gave me 10 milliamps. I'd have to go back to that video to see what it was. But if I change this to 100 ohms, that would knock the current down to about 6.5 milliamps. Now under that condition, I need to make sure I can still drive the output to its full capability, plus still have a little bit of surplus current. So now I need to set up a little test and see how that works out. So what I've done is hooked up the upper part of the output stage on the breadboard, and I connected it to the power supply. This is what the circuit looks like. I have a current limiting resistor so I can hook my other supply up and adjust the voltage until I get the right amount of current going into the base, and I can measure the gain of this and make sure that I have enough current going into the base here to drive this output to whatever capability I need. What exactly capability would I need, by the way? Well, I want this amplifier to be able to handle 4 ohm loads, and it should be able to do around 100 watts into 4 ohm loads. So if you do the math, 100 divided by 4 ohms is 25, and we take the square root of that, 5 amps RMS. Now the amplifier has to deal with a sine wave which has its peaks, and at some point on that sine wave it's going to be at that peak, and the amplifier needs to deal with that peak current. So I have to take 5 amps times the square root of 2, which gives me 7.1, or we'll just say 7 amps. But you know, in the real world there will be some reactance in the load and everything. We'll just say 10. Just make it an easy number to deal with. We'll just say 10 amps. Okay, I have the power supply hooked up here, just reading the power supply's meter. I have this bulb here. It's a 12 volt 27 watt bulb, and I'll monitor the current here. I have the power supply on. I adjusted the power supply so when that bulb is on I get exactly 2 amps flowing through it, and that came up to about 4.5 or 14.5 volts. There's some drop across the transistor and the emitter resistor. I had to set the output stage up including those because they do affect the gain of the circuit. If you watch my Darlington transistor and Z-Cli pair transistor circuits where I discuss the gain and why they need the discharge resistor and how it does affect the gain, you might want to take a look at those videos. Now I have this 10K resistor here to limit current because I have this directly hooked up to my other power supply, and I'm going to increase the voltage, and when I get 10 volts across this resistor I know that 1 milliamp is flowing. Yeah, I could hook the meter up in series and set it to the current measuring range, but I'm just going to just measure the voltage across that. Yeah, same difference. Okay, let's fire it up. So the bulb comes on full brightness, and I do have 10 volts across that 10K resistor. Collector current is at 2 amps. The bulb is nice and bright. And I'll just let it sit and run here. I'm just kind of curious how things will warm up. This is pretty cool. Maybe warming up slightly. This transistor is really cold. This resistor, a little heat to it, not much. Okay, well I let this set and run for a while and nothing got really hot. I mean, this is running near saturation. The output transistor can't actually saturate in a Darlington configuration. So I just wanted to see how much heat would build up. Nothing got seriously warm. So now what I want to do is start adjusting this current down going into the base until this bulb starts dropping out, and then see what the current going into the base is to get that 2 amps. Okay, turn that on. So adjust that down and you can see it drops out. So let me adjust that. The meter says 2 amps again. There's only 1.8 volts across that. Okay, so if I'm putting 1.8 volts across that resistor, that's 180 microamps. So if I take 2 amps divided by 180 microamps, that gives me a gain of 11,111. Really, that much? That is quite a bit of gain. Wasn't expecting that much gain. I know the gain of these output transistors is about 100. These vary quite a bit. Let me pop that out, pop it in the tester here. See what this thing says it is. Of course, this will be at pretty low current, I would think. Oh, 218. Oh, this has pretty high gain. So, you know, at low currents, you know, the gain of a Darlington circuit is this gain times this gain plus this gain plus this gain. So, yeah, it's actually 20,000 plus. But, you know, with the speed up resistor here, and maybe a little from the emitter resistor, we do lose some gain. So yeah, that's pretty darn high. So would that be enough at 10 amps? I don't really have 10 amp supply. Plus things would start melting on the socket board. It's not really rated for 10 amps. And 10 amps continuous through this resistor is probably not a good thing. At higher currents, these transistors will drop. And I looked at their data sheet. At 10 amps, they're still very good. You know, a lot of older power transistors can drop off to a gain of under 20, sometimes under 10. But these are very nice linear gain audio transistors. What's known as beta droop. As the current increases, the gain starts to droop off. These don't drop off as much, and they still have a gain of around 50 or so at the operating temperature of the amplifier. As I said before, these little transistors are the same as these, just in a smaller package. It can't dissipate as much heat, but it's the same transistor. The transistor I'm going to use in the finished amp, of course, will be these. Much bigger, better power dissipation. So if we figure the gain drops to we'll just say 40, and the gain of these drop down as well, you know, maybe to 100 at higher currents. Yeah, data sheet doesn't show the gain curves of these. It's kind of unfortunate. You know, at 10 amps, if the gain is still around 50, these won't have to push much current at all. Matter of fact, to see 10 divided by 50, 1/10 of an amp. If these transistors drop to a gain of 50, well, we'll just use our example, a gain of 40, these won't have to push much current. These won't have a lot of current through them. They only have 1/4 of an amp, so the gain shouldn't drop off too much with these. So if our gain drops off to 3,000, take 10 divided by 3,000. Yeah, we'll only need 3 1/3 milliamps of drive current. So we still have plenty extra. Yeah, so running it at 10 was just excessive. So backing it down to about 6.5, I think it's a good idea. What I'll do is I'll probably set this up in LT Spice or some program and you know, do some tests that way and see how it performs. Well, it turns out this transistor, which was in the circuit, is a special case. I bought it at a different time. It must have been from a high gain bin. That's why I'm getting 200 and something. And these other transistors are the latest ones I bought. I measured several of them, and they have a gain of in the range of 110 to 125 or so. This output transistor is a type R, and it has a gain of around 82 or something like that. Just measured with this thing. Of course, it's going to be at low current. So I put one of the other transistors that have a lower gain in place and run the test again, adjust it till we find the dropout voltage, and the meter turned off, and let me adjust that. Okay, right around, go up a little bit, right around 300 microamps now. See, the other one was 180 microamps, so you can see now with the lower gain transistor we have to put more current in to get this output. Well, the thing of it is, if I use these transistors, these are the O grades. It's a higher gain. These have over 100. I'll have to look at the data sheets. Yeah, it's a little over 100. These, like I say, are type R's that have gains of under 100. So I need to make sure that I'm still going to have enough gain at high current. So I need to see what these things, how their gain is at around 1/4 of an ampere of collector current. Okay, I decided I wanted to continue and get closure on this. So I took the circuit off the socket board and put it on the perf board so I could run more current through it. I have a fatter resistor, and now I have these two bulbs in parallel. This is a 50 watt bulb, I think, and the other one, so it should draw about 6 amps. I paralleled the supply, so we'll get 6 amps, or 6.4 amps maximum. Now I'm measuring current here. So if I turn on the supply, well, it's already on, but turn on the other supply and adjust it. I got to do this quick because this heats up pretty quick, putting that much current through it. And I'll measure the gain. So I turn it on and we get nice bright lights here. We're almost at 6 amps. You have to add those channels together. We're pushing 1.26. So let me turn this off. And yep, it heats up quick. Okay, so let me punch that up on the calculator here. So it was about 6 amps. It wasn't quite, but just use 6. 6 divided by 1.2 something. We'll just say 1.2. And exponent minus 3 because it's milliamps. A gain of 5,000. Now we still have plenty of gain. I did put the lower gain transistor in here. So, 6 amps and we're only putting in 1.2 milliamps. I would expect at 10 amps we wouldn't put any more than 3 milliamps. So, yeah, running that output at 6.5 milliamps should be just fine. Those transistors will be cool. Perhaps distortion will be lower. I probably should test the PNP side, the bottom side as well, but I don't suspect it would be too awfully different. So at this point I'm going to wrap it up. Thanks for watching.